Welcome to this webinar on nuclear fusion and the TOMAS project. My name is Christel Crombé and I'm working at the physics laboratory in the academy. I will share the webinar today with my colleague Andrei Goryaev. The first part of the talk is a crash course on nuclear fusion and why we are doing so much effort to realize it on Earth. It is about 60 years that scientists are now working on this, and I will try to explain the basic principles in 15 minutes. First, a motivation. Why a new energy source? I think I do not have to convince you of the need. It is well known that the energy consumption has grown strongly over the past decades. In fact, it has increased by 50% since 1973. And it is predicted to grow by another 60% by 2030. And what are the sources? In fact, the options are limited. There are only 3 at the moment. With nuclear fusion, there might be a 4th option in future. Option 1 are fossil fuels. They work, but we realize in the meantime that we need to do something about CO2. And solutions could be CO2 capture or storage, but these things still need to be developed on a large scale. Option 2 are renewables. Yes, they work, but they have a low efficiency. There is a problem of intermittency and storage, and these are still open questions. These points nevertheless are crucial if you are increasing the total fraction of renewables in your energy mix. Up to now it's of the order of 10-20%, and the unpredictability of the availability is, let's say, still easy to deal with. But the story will be different when you rely on renewables as your major energy source, when it becomes the backbone of a country's energy production. And we are used to having electricity available all the time. Option 3 is nuclear fission, a very robust system, a reliable production, but big issue there, also here in Belgium now, is the acceptability by the general public. And then possibly we will have a 4th option, nuclear fusion. And there it still needs to be demonstrated that it's scientifically and technologically feasible. And in that aspect, the laboratory of the military school here is contributing. Whatever we do, we will have to do it on a massive scale, and it has to be carbon-free. Why nuclear fusion? Well, it has many advantages. It can be a new energy source with a massive, predictable and potentially continuous or variable power. It can complement renewable energy sources. It is safe. Accidents like Chernobyl or Fukushima cannot happen, and it's environmentally responsible. It has an almost limitless supply of fuel for at least hundreds of millions of years. And the fuel is widely distributed around the globe. The fuel in the present configuration is deuterium and lithium. There are no CO2 or other greenhouse gases produced, and it has no long-lasting, highly active radioactive waste. It was mentioned for the first time during the COP26 summit as a potential energy source. Currently, 1/3 of the total primary energy production is for electricity, and this will grow. In Europe, we know that governments are pushing very strongly for electrification, electric heating of houses, electric cars, electrification of industry. The International Energy Agency anticipates that the total demand for electricity will grow by 80% by 2040. 1/3 of this will be for China, 15% for India. And electricity is the main vector of social and economic development. Another thing you may not realize is that still 1.6 billion of people need to connect to an electricity grid, so there is no electricity available at all in large areas of Africa, China and India. And this will change, and also it's our duty as humans to make this change happen, because as I said, it's the prerequisite for economical and social growth. It is clear the 4th option, nuclear fusion, in the energy mix will be very welcome. And now first some physics background. So what is the principle? The physics principle is rather simple. When we make a graph with a binding energy per nucleon for the different elements in nature, we see there is a maximum around the element nickel, which has the highest binding energy and thus is the most stable element. All elements lighter will become more stable when they transform to heavier particles. These are the elements on the left-hand side of the nickel. And for them, it's now the opposite is true than for the elements on the right-hand side, the heavier elements. For them, it is energetically better to transform into lighter elements, hence fission, nuclear fission. This is in fact the opposite of nuclear fusion. In both cases, the gain in energy comes from a difference in mass, and according to the famous formula of Einstein, this small difference in mass is transformed into a huge amount of energy. And this is exactly the strength and the reason for the high efficiency of nuclear reactions, both fission and fusion. Now zooming in a little on the left-hand side, on the light elements of the periodic table, hydrogen, helium, lithium, carbon, then we see on this graph that helium-4 stands out. It is a very stable element. You notice a big jump from deuterium and tritium, which are isotopes of hydrogen and helium-3, to helium-4. Also very stable are carbon-12 and oxygen-16. This has to do, in all cases, with the atomic structure of the elements. But the message here is that if we are looking for an efficient reaction, it's a clever idea to look for a reaction that produces one of these very stable elements. And this is exactly what we do. So we have a reaction that produces this helium-4. So we gain a lot of energy. The best example is the sun, because nuclear fusion is the energy source of the sun and the stars in the universe. So let's look at the sun, what happens there. Also there, helium-4, the very stable element, is produced. But in the first stages, the first things that happen is a transform. So you start, in fact, there from hydrogen, a proton nucleus. And the first thing that happens is you first have to transform this proton into a neutron, which is called inverse beta decay. And this is a very slow process. It has a low efficiency. And in fact, for us, mankind, this is good news because it means the sun is not burning the fuel quickly. So there is time on Earth for life to develop and for intelligent life to develop. So the low efficiency of this reaction in the sun is in fact good news for us, but it's not good news if you want to use it in a reactor. It would be not possible to make an efficient reactor out of this reaction in the sun. So we have to play a little trick there. But inspiration comes indeed from the energy source of the sun. Of course, I say it has a low efficiency, but this is of course relative because the sun is so massive, it's big, and still there every second 4 million ton of mass is transformed into energy. So the sun becomes lighter by 4 million ton every second. And another thing you need to know is that if you want to realize nuclear fusion, it always means bringing together nuclei with a positive charge in a very small proximity. So these positive charges will repel each other. So you have to overcome this Coulomb repulsion. That means that you will have to work in high temperatures. For the sun, the center is of the order of 15 million degrees. For our fusion reactors, we will be higher even because we use a different reaction. So it will be 10 times higher and hotter than the sun. So what is the solution for our nuclear reactor on Earth? We need to be more efficient than the sun. And we can do this by skipping the inverse beta decay part of the process, because that is the part that makes the reaction in the sun very slow. So instead we can start from isotopes of hydrogen, not pure hydrogen, but isotopes which have already a neutron inside. These isotopes exist. These are deuterium and tritium. Deuterium has one neutron and one proton. It is part of water on Earth. Also, the water that you drink has a small fraction of deuterium inside. It's perfectly safe. Your body does not notice. Tritium, on the other hand, has one proton and two neutrons. is not available in nature. It has a half-life of 12.3 years, and it has to be made for your reaction. It can be made out of lithium by bombarding lithium with a neutron. And lithium, as you know, is used nowadays in batteries, in your laptop, mobile phone, in the car. So lithium is widely available, and the same is true for deuterium. Also there is plenty of supply. Deuterium and tritium then fuse together, produce helium-4 and a neutron and a lot of energy. Also note that the division of energy between the reaction products is inversely proportional to the mass. This is the conservation law of impulse. So the helium-4 has 20% of the energy and 80% of the mass, and the neutron has 20% of the mass, 80% of the energy. For the deuterium-tritium reaction, the reaction rate is highest at 200 million degrees. Remember, the central temperature of the sun was 15 million degrees, so this is 10 times more. Our reactors will thus be hotter than the center of the sun. And the total energy gain is about a factor of 1,000. So you start from 20 kilo electron volt and you end up with 17.6 mega electron volt. So we have chosen the reaction. It's the most easy one. Now we can build a reactor. But there, the first question already comes. How are you going to confine your plasma of 150 million degrees in a reactor? There is no material that can withstand 100 million degrees, so we have to use something else. And the left picture is a cartoon of a neutral gas, which is what you start from. You buy a bottle of deuterium, you buy a bottle of tritium, and you inject it in a vacuum chamber, and then you heat. I will show you in a minute how we can do that. And when you continue heating, at a certain point, electrons will separate from the nuclei, and you will have what is called a plasma, so a soup of negative electrons and positive ions. When you then apply a magnetic field to these particles, they will start to follow the magnetic field lines because they are charged, and there is a Lorentz force that will force them to make a gyration around magnetic field lines. You can see for the cylinder, in the straight part of the cylinder, the particles do not escape anymore, so they nicely follow your field lines. They are what we call confined. But of course, the edges still have a problem because there you will lose your particles. So a straight cylinder is not a good solution, but is a starting point. So a solution is then to bend the cylinder on itself and to make a donut shape, a toroidal configuration. And there you just close the ends, and you do not lose the particles anymore. They come back. So the charged particles here, the electrons, deuterium, tritium, and also the helium-4 that is produced, they're all charged particles. They're all nicely confined in your donut. The neutron, that's a different story. The neutron has no charge, so it can escape, but it's also good because it's a way to extract the energy out of your reactor. But the charged particles will stay in the donut. So it's not completely true because of the bending of the donut, the magnetic field is not homogeneous anymore, and you create additional losses, additional drifts, where you, after a certain moment, you will also lose particles. So this simple toroidal configuration is not a good solution. It has to be a bit more complicated. There are two solutions for that. So in both cases, what you do is you create an additional magnetic field, what we call a helical field, so a twisted magnetic field, a combination of the toroidal and a poloidal field. And the two solutions, but I have no time to go into detail, are called tokamak and stellarator. Tokamak is based on a transformer. So there you create a plasma current, and the current produces the second part of the magnetic field. Because of this transformer action, this machine has to be operated in a pulsed modus. And it's the configuration that is most widely developed and will be used for the future reactor ITER. It has proven its strong capabilities. But there is also a second option, developed in parallel. And there, the trick is that you get rid of the transformer and you produce this helical twisted field in a different way, in fact, by shaping the coils in this weird shape that you could see, the blue shape here, produces immediately the right magnetic field with a helical twist. And this configuration is the basis of a big machine in the north of Germany, in Greifswald, Wendelstein 7X, and also there the laboratory has contributions. So this is a different solution for the same problem. So we create in both cases a helical magnetic field, and in that way we can confine the particles. So we have a reactor, we have a reaction, we have a confinement, but we still need to get our temperatures of 100, 200 million degrees. How are we going to do this? Well, there are different methods, and the machines nowadays mostly use a combination of different methods. First, you have ohmic heating. Ohmic heating is based on resistivity. Energy is dissipated in the plasma. The same is true for a copper wire. When you run a current through the copper wire, it will heat due to resistivity. The same happens in the plasma, but it can only happen when there is a current in the plasma. So you immediately notice it is only applicable for the tokamak configuration. In the stellarator, the ohmic heating part is almost non-existent because there is almost no current in the stellarator. In any case, also for the tokamak, ohmic heating only is not enough to reach our 100 million degrees. We will have to use additional methods. One of the additional heating methods is the injection of electromagnetic waves. It's like a microwave oven. In our case, the frequency of the waves is adapted to the gyration frequency of the charged particles, either electrons or ions. When we want to be resonant to the electron frequency, we have to make antennas in the range of gigahertz. It's like microwave range. Of course, when we want to heat the ions, they are much heavier, and there the frequency will have to be lower in the range of megahertz, so radio waves. And it is exactly that aspect that the Laboratory of Plasma Physics is specialized in. So it makes antennas for heating of ions in different machines. Moreover, the Wendelstein 7X stellarator. Another additional heating mechanism is the injection of a very hot beam of neutral atoms, deuterium or tritium atoms mostly. It can be compared to the steam pipe for steam of your cappuccino. It's a way to heat very efficiently the center of your cappuccino, and this is the same what we will do. We will try to heat the center of the plasma. Of course, depending on the size and the magnetic field, these neutral atoms have to be very energetic, because you want to reach the center, you do not want to heat the edge. To reach the center, we'll have to have neutral atoms that have an energy of the order of 100 kilovolt or even megavolt. And in fact, both additional heating methods, neutral beam heating and wave heating, are very specialized, but I have no time in this webinar to go into more details of these heating mechanisms. Lastly, when you realize your fusion reactor, you have a bonus heating. The bonus heating comes from the helium. It is a charged particle, it's produced in the reaction, and it carries 20%, 3.5 mega electron volt, 20% of the energy, and it is charged, so it will stay in your plasma, and it's a way to keep the fire burning. But this only happens once you have already realized your fusion reaction. So this is the summary of my crash course on nuclear fusion. Yes, we can and we do realize nuclear fusion on Earth. The physics principle is proven. We can do it, we can control it. You need a plasma of deuterium and tritium. You need to heat it to 150 million degrees, confine it by magnetic fields, and then helium particles are produced that sustain the burning plasma. Neutrons still escape the magnetic field and transfer the energy to a blanket around the torus. And then, but this is not yet the case in the present experimental machines, but then for fusion power plants, these neutrons will heat a steam generator and will be like in a conventional power plant. There the heat will be transformed into electricity. And because the fact that you're working with a nuclear reaction, it's very, very efficient. You only need a small amount of fuel. In fact, 1 gram of fuel is equivalent to 8 tons of oil. So then I now pass on to my colleague, Andrei Goraev, for the second part of the talk.
Hello everyone. The second part of this webinar is dedicated to the TOMAS project description and the wall conditioning studies for fusion machines. We'll talk about wall conditioning methods, the purpose of wall conditioning, and how wall conditioning affects the plasma performance in the fusion devices. In real fusion machines, plasma particles still interact with the surrounding walls. Due to charge exchange processes in plasma, newly created particles are not subjected to the magnetic field and can quickly leave the plasma volume, colliding with the walls. It can lead to few adverse effects. For example, if the walls are dirty, like containing a lot of trapped impurities, the escape in charge exchange neutrals can cause its release to the plasma volume. Heavily impurities inside the plasma radiate the power faster than we hit the plasma, leading to radiative collapses, sudden discharge termination. The fuel itself can be stored on the wall surfaces. When it's released during the consequent plasma discharges, it makes it hard to control the fuel species ratio and the plasma density. All these adverse effects significantly reduce the plasma performance. To avoid this, we need to clean the walls of the fusion reactors before by using various methods called wall conditioning. Several types of wall conditioning techniques are applied in certain reactor conditions depending on the technical configuration and device status. Each wall conditioning type employs its underlying physics method. We can divide wall conditioning techniques into 3 categories. The first one is baking. Here we accelerate the removal of impurities by heating the walls, and it's based on the temperature-induced desorption mechanism. The second type is based on the particle-induced desorption mechanism. We use auxiliary plasmas to create a particle flux to the wall, which stimulates the removal of the trapped impurities of UL species. Different type of plasma discharges are employed depending on device conditions. The last type of wall conditioning is thin film deposition. The idea is to coat the walls with thin films of certain materials to trap the impurity chemically or to coat them. So they cannot be released during normal plasma operation. Again, we also have various techniques based on the available equipment. Another critical point for wall conditioning is the presence of the magnetic field. In large superconducting devices, the magnetic field cannot be switched off quickly. So we need to know which technique we employ during the field's operation and which techniques are available only during the maintenance period. For example, we can use baking, glow discharge cleaning, or wall coating only before or after plasma operation, overnights, or during weekends. In contrast, some techniques like radiofrequency plasma conditioning and wall coating via radiofrequency plasma must be applied while the magnetic field is on. Combining both types of wall conditioning concerning the experimental timeline leads to the most efficient cleaning result and better plasma performance. The wall conditioning techniques have to be individually optimized for each fusion device. Large superconducting devices like ITER or Wendelstein 7X have very limited time for this type of optimization. However, some smaller devices with a flexible experimental environment fully suited for wall conditioning optimization can be used to support studies for large fusion devices. Laboratory for Plasma Physics of Royal Military Academy entirely operates the TOMAS device, which is precisely suitable for wall conditioning optimization. The TOMAS device is a toroidal stainless steel device with a major radius of 78 centimeters, which is the distance from the device center to the center of the plasma chamber. It has a minor radius of 26 centimeters, which is the vacuum chamber radius. The vacuum vessel can be baked out with an average temperature of 80 degrees Celsius, allowing for baking studies. The device has 16 toroidal magnetic field coils, providing a magnetic field of up to 125 millitesla on the device axis. It's in the middle of the vacuum chamber. The device has 3 plasma heating systems: glow discharge, electron cyclotron resonance heating system, and ion cyclotron range and frequency system. These systems allows for study of glow discharge cleaning and radio frequency plasma conditioning. The TOMAS device is also a test bed for plasma wall interaction and plasma production studies. TOMAS is equipped with various plasma diagnostics, which makes it an excellent training tool for students and young researchers to obtain the necessary experience in experimental physics and engineering. The TOMAS device is located in the Research Center Jülich in Germany. The device is operated by our team from the Laboratory for Plasma Physics of Royal Military Academy in collaboration with the Institute for Energy and Climate Research of Forschungszentrum Jülich, Germany, the Royal Institute of Technology in Sweden, and the Kharkiv Institute for Plasma and Technologies in Ukraine. The TOMAS project also receives an extensive support from the Max Planck Institute for Plasma Physics in Germany, Ghent University in Belgium, and the ITER organization. Our team has an extensive list of research topics connected to the TOMAS project. We aim to provide detailed studies of the radio frequency wall conditioning plasma, including electron cyclotron wall conditioning, ion cyclotron wall conditioning, and the mix of electron cyclotron and ion cyclotron plasma at variation of experimental parameters such as working gases, gas pressure, magnetic field, electron cyclotron and ion cyclotron input power, ion cyclotron frequency, all of this using available TOMAS diagnostics. We support numerical modeling of electron cyclotron and ion cyclotron wall conditioning plasma and experimental model validation. It's also essential for us to contribute to plasma-facing component material erosion studies, isotope exchange studies, and impurity removal studies by exposing material samples to different types of wall conditioning plasma in the TOMAS device. Our collaborators help us with characterization and postmortem analysis of exposed material samples using various surface analysis methods. As we already mentioned, the TOMAS device is equipped with various diagnostics providing experimental flexibility for wall conditioning studies. Among the diagnostics, we have movable landmark probes allowing for measurements of electron density, temperature, plasma potential along the radius in horizontal and vertical planes, time-of-flight neutral particle analyzer capable to obtain thermal and charge exchange neutral particle energy spectra, quadruple mass spectrometer providing residual gas content and time evolution of impurity concentrations, residual field energy analyzer allowing for recording of local ion energy distribution functions, optical spectrometer for plasma density and temperature evaluation and tracing impurities, visible cameras and fast cameras to monitor plasma events, extracting information about the absorption and propagation of waves in plasma, and a microwave interferometer allowing for continuous line integrated density measurements. One of the wall conditioning techniques studied in TOMAS is glow discharge cleaning. It's a hollow cathode discharge where the anode is specially built based on the required discharge properties. It's usually very small, while the cathode is the whole wall of the machine. By applying the potential difference between these electrodes, we accelerate plasma ions toward the wall. Ions bombarding the wall stimulate the release of impurities, which are further pumped out from the vacuum vessel. The glow discharge anode of TOMAS is the same as anode for large fusion devices such as Wendelstein 7X and ASDIX upgrade. It allows for easier extrapolation of glow discharge optimization results. The optimization is done by increasing the impurity removal rates through the variation of glow discharge parameters such as working gas pressure and anode current. We also have to take into account the adverse effect of glow discharge for the optimization of this procedure. The glow discharge optimization also requires improvement of glow discharge homogeneity and stability. It means that the discharge should not be localized in any vessel structures, and the current voltage characteristic should not contain any oscillation to prevent arcing. Moreover, the working gas plays a significant role in low discharge cleaning optimization. Hydrogen is more suitable for impurity removal. You can see an example of hydrogen glow discharge cleaning in Wendelstein 7X. The dominated impurities such as water, methane, and carbon oxides are significantly reduced in the residual gas content during the glow discharge application. Additionally, it's worth noting that every impurity removal rate follows a certain exponential time trend. As a carrier gas, helium is more effective for fuel hydrogen removal from the walls. Electron cyclotron wall conditioning is a wall conditioning technique that requires the presence of a magnetic field. It's a plasma-based technique that works on the principle of microwave absorption and cyclotron resonance conditions, when the wave frequency or its harmonics is equal to the rotational frequency of electrons in the magnetic field. In the TOMAS device, a magnetron with a fixed frequency provides these conditions. Depending on the plasma parameters, we can either create strong ion fluxes towards some part of the wall or charge exchange neutral particles equally distributed to all wall surfaces. These generated particles are used for impurity and fuel release in the same manner as glow discharge cleaning. Understanding all mechanisms of wave absorption and propagation is important to regulating particle fluxes and energy and minimizing adverse effects, in particular stray radiation. To achieve this, we use Landmer probe spectroscopy and video diagnostics to collect information about plasma, temperature, and density distributions. Various scans are performed at different pressures, magnetic fields, electron-cyclotron input power, and wave polarization. For example, you can see the results of quasi 2D temperature and density scans done by our PhD and master students. We can define these parameters spatial distribution and time evolution. These experimental results are used as a basis for the theoretical prediction of electron-cyclotron wave propagation, absorption, and conversion mechanisms. One of the examples of electron-cyclotron wall conditioning in TOMAS shows its application in removing water from the walls using hydrogen and helium. The conditioning is performed in a pulse regime with 5-second discharges and 55 seconds of dwell time to allow for pumping out the removed water. The pulsed operation shows better cleaning performance because it minimizes the redeposition of released impurities back to the walls. In this particular case, pulsed electron-cyclotron wall conditioning in helium is more efficient for removing water from the stainless steel wall of TOMAS. Ion cyclotron wall conditioning uses fluxes of charge exchange neutrals created in plasma for wall cleaning. Ion cyclotron wall conditioning is based on the ion cyclotron resonance heating of plasma. In this case, the energy is transferred mainly to ions using the cyclotron resonance mechanism. However, this type of heating requires an antenna in the matching circuit to deliver the radio frequency power to the plasma. In the TOMAS device, we use so-called ion cyclotron region frequency system, since with the low magnetic field we can only use the harmonic heatings of the plasma. It is worth noticing that we use a novel additive manufacturing approach to make IC antenna. The antenna was 3D printed at Inconel and then coated with a thin layer of copper to improve its surface conductivity. The matching circuit, consistent of 3 variable capacitors, reduces the reflected power back to the generator. To properly understand the dependence of the ion cyclotron wall conditioning plasma cleaning efficiency on the plasma parameters, we need to characterize the plasma. One of our PhD students did it. He studies the dependence of electron density and temperature, energy distribution of ion and neutrals in ion cyclotron wall conditioning plasma concerning neutral gas pressure, radio frequency, power frequency, and the magnetic field. These data used to numerically model the RF wave absorption and propagation in plasma to optimize wall conditioning effects further. You can see part of his work as an example. This picture shows how the radial distribution of electron density and temperature vary when we change the magnetic field and pressure while keeping other parameters constant. Another feature of the TOMAS device is the possibility of exposing material samples to different types of plasma. This allows us to contribute to plasma wall interaction studies. The device is equipped with a sample load log system consisting of a sample chamber, vacuum manipulator, and sample holder. We can expose up to 8 samples simultaneously in almost free orientation of the sample surface inside the plasma. In particular, we are interested in horizontal and vertical exposure to mimic specific wall structures. The samples can be actively heated, which expands experimental conditions, and the sample node lock system allows for exposure of any vacuum-compatible materials. One of the sample exposure applications is to study impurity concentration changes in the sample surface layers during exposure to different types of wall conditioning plasma. It's also part of the wall conditioning optimization task. Our colleagues from the Research Center Jülich in Germany and the Royal Institute of Technology in Sweden help us to obtain information about the impurity concentrations and surface layer structures of exposed samples. We have two PhD students working on these topics. Here some results of their work are presented. We exposed samples made of graphite wall panels of texture tokamak to glow discharge cleaning plasma and to ion cyclotron wall conditioning plasmas. What we find out is change in the plasma parameters increases the removal rates of species from the co-deposits on the samples. This also allows us to show how the concentration of trapped deuterium changes after exposure to the wall conditioning plasma in different input power and working gases. The third type of wall conditioning technique is thin film deposition. It allows us to trap oxygen by forming a stable oxide. This reduces oxygen sputtering and erosion of the wall material. Moreover, a thin layer can cover the existing impurities, preventing their easy release from the wall. The deposited thin layers also reduce fuel recycling, improving plasma density control. And all these effects can significantly improve the plasma performance. The most common thin deposition technique is barnization. It involves coating walls with a layer of boron. Currently, this type of wall conditioning can be done directly on TOMAS due to some safety restrictions. However, we can contribute to studies of boron layer erosion using our machine. The problem is that the deposited boron layer is eroded during the consequent plasma experiments. By exposing the boron-coated material samples to the TOMAS wall conditioning plasma, we can estimate the erosion rates of boron layers and extrapolate them to large fusion device operation scenarios. Here we see an example of boron layer erosion in helium-ion cyclotron wall conditioning plasma at a frequency of 25 MHz and an input power of 2 kilowatts. There were two exposures, each lasting 24 minutes. In the first exposure, we placed the samples horizontally at the plasma edge, and in the second exposure, vertically in the plasma center. So we exposed two graphite boron samples in each exposure. We measured the boron layer thicknesses before and after the exposure, and the results are shown in the figures. Knowing the layer thickness difference and exposure duration allows for calculating erosion rates. These results validate the numerical modeling of erosion based on the plasma parameters. It's interesting to see here that the erosion was homogeneous in the case of horizontal exposure. We can see the deviation of erosion rates with respect to the sample location for the vertical exposure, which is due to inhomogeneous plasma profile along the vertical axis. To summarize our talk, we would like to say that there is a strong progress in nuclear fusion research for energy production. Nuclear fusion can become an important player in the future mixed energy market. However, it's important to have a good control of inner wall conditions of the future fusion device to achieve plasma stability and high performance operation. To do this, there are different wall conditioning methods. The wall conditioning is individual for every fusion machine and requires optimization. The TOMAS device is an ideal testbed for wall conditioning optimization studies. It has all necessary equipment, including plasma production and heating systems and various operational diagnostics. The device can provide significant experimental time. Our team has strong collaboration with different laboratories and institutes in Europe. We are also expanding our list of collaborators to Australia. So we have plenty of opportunities for master and PhD students to do their work in physics and engineering. In the last slides, we show you the list of recent publications we made on the mentioned topics during the last 3 years. We think it directly reflects the progress of our studies. Thank you very much for your attention.